Lecture problem 5. A 10.0 kilogram box starts from rest at the top of an incline and travels down a 4.0 meters long inclined plane. The incline makes an angle of 37 degrees with the horizontal. The coefficient of friction between the box and the incline is 0.400. Determine the work done by friction. This question is not that much different from the previous one that we have solved, except that this one is providing the coefficient of friction instead of the final speed. For that reason, the approach that we're going to use is going to be slightly different. As usual, the first thing that we need to do is to put together a free body diagram. The box is under three forces. The weight mg is pointing vertically downward. The normal force is acting in a perpendicular form with the incline, that's Fn, and the kinetic friction force is acting up the incline in the opposite direction of motion. This is the Fk. The next thing that we need to set up for the free body diagram is the system coordinate, and since the mass is accelerating down the incline, we're going to line up the x-axis with the inclined plane and therefore the acceleration. Notice that the angle that the weight mg makes with the y-axis is also 37 degrees. Now, to be able to solve for the work done by the friction force, there are two different ways. You could use the work done by the net force, that equals to the change of kinetic energy, or the work done by the non-conservative forces equal the change in Ke plus the change in Pe. These two equations are the same. You can choose to use one or the other. I happen to like the second one. There is another way that you can use to solve for the work done by the friction, which is the work done by the friction force, which is known to be a constant force, that must equal to the friction force times the displacement times cosine the angle of 180. Remember that the friction force always makes an angle of 180 with the displacement. In this example, because the final speed is not known to us, evaluating the change in kinetic energy will require you to use not only the dynamics of Newton's laws, but also kinematics, and the process is going to be very long. However, using the work done by the friction force as a constant force equal Fk times the displacement times cosine 180 is going to be much quicker and easier. As you see, the only missing information is the friction force Fk, and that can be obtained from the dynamics of Newton's laws. The sum of the forces acting on the box equal the mass of the box times the acceleration. There are three forces: the normal force, the friction force, and the weight mg. They all add up to the mass times the acceleration. Now let's break this equation into components. The x component first. The normal force is lined up with the y-axis, therefore its component along the x is 0. The friction force is lined up with the x-axis and pointing in the negative direction, therefore negative Fk. The weight mg needs to be broken into two components. The y component is equal to negative mg cosine the angle 37, which I'm going to call theta, and the x component is positive mg sine the angle of 37, which also I'm going to call theta here. Therefore, the x component is going to be positive mg sine theta. That's going to equal the mass times the acceleration, because the acceleration is lined up with the x-axis. The y component now. The y component will include the normal force, because the normal force is lined up with the y-axis and pointing towards the positive. The Fk has no component along the x, therefore 0. The weight mg has a negative component, which is negative mg cosine theta. There is no acceleration along the y, therefore this is going to be 0. Notice that the y component allows you to isolate the normal force to equal mg cosine theta. Since the coefficient of friction is given to us, therefore the kinetic friction force Fk is going to equal mu k times Fn. Substitute Fn by its expression, you obtain mu k times mg cosine theta. Now, let's substitute this expression in our work equation, which says work done by the friction force equal the friction force times the displacement times cosine 180. The cosine of 180 equals -1. Making the substitutions for Fk, we obtain the work done by the friction force to equal, instead of Fk, we write down mu k mg cosine theta times the displacement d times -1. That comes from the cosine 180. Rearranging this equation, we obtain the work done by the friction force to equal negative mu k mg d cosine the angle theta, which is the angle of the incline. Solving for the work done by the friction force, we obtain negative 125 joules.